Welcome to Real Civil YouTube channel. In this video, I am going to explain linear time history analysis in ETABS software. So previously, we have done the seismic analysis using equivalent static and response spectrum method. And now, in this video, we are going to cover linear time history analysis. So let's begin. So our first step is we have to define our time history function. Okay, so there are many options available. If you want to analyze the building with a time history record which is not by default in ETAB, then you can go with users. Okay, but in this video I am going to show you. We'll take one file from ETAB. ETAB has provided some time histories, some ground motions. So I will show you how to use those and analyze our structure. So go to add new function. So first of all, we'll browse. Okay. So these time histories are available in C drive, program files, computer and structures, ETABS 19, time history function. So these are the different time histories are available in ETABS software. So we'll choose the first one, Altadena earthquake. Okay, so you can see basically there are three, that is x direction, y direction and z direction. Ground motions are there. Similarly for each earthquake, if you want different time history functions other than this, then you need to download it from websites. There are many websites available. You can click on I button or you can go to description box. I have shown how to download those time histories. Okay, then you can use. So first of all, select the time history, click on open. Okay, before proceeding, we need to check the file. So I will go and open that file. So this is the file which we imported. Okay, so this is the file. So here you can see some data is given. Okay, like the units are centimeter per second square. Okay, all these points, the acceleration is recorded at 0.020 second interval. Okay, and there are 2000 points of acceleration data. So all there are actually total 2000 number of points are there, which are equally spaced at 0.020 second. Okay, now here we have to put some information. So first of all, we need to give the name, that is ground motion, Altadena x direction, header line to skip. So actual acceleration point starts from here. Okay, so first two lines, this is the information. So we need to skip these two lines from our analysis. So here we will keep two prefix characters per line to skip. So there are no any prefix characteristics. So keep it 0. Number of points per line. So count these points: 1, 2, 3, 4, 5, 6, 7 and 8. That means there are 8 number of points per line. Okay, so keep it 8, or if there is different number you can type 8. Value at equal interval of, so here the values are 0.020 seconds, so 0.020 second is the interval. Okay, so this is the user defined. Okay, no problem. So this is the x direction earthquake. Okay, now we'll add the y direction as well. We'll check the file once again. Again the same things are there. Okay, so ground motion, Altadena, y direction 208. Okay, similarly z direction, ground motion z. We'll check the file. Two lines to skip. 0.020, 1 2 3 4 5 6 7 8. Okay, so no need to change anything. Click on OK. So we have added the different time history functions. Okay, here there is option that is view response spectrum. Okay, so for every earthquake record has its own response spectra. Okay, so here you can check. Basically for RCC building we consider the damping ratio of 0.05, so remaining you can delete. Okay, so here you can see this is the response spectra or response spectrum plot of this ground motion. Okay, similarly this is the response spectrum curve for the ground motion y, and this is the response spectrum curve for the ground motion z. So here you can see x direction, the acceleration is 1.55 into 10 raised to 3, and here is 665 612. So most stronger earthquake we can say was along x direction. So click on OK. Now the next step, which is very important, the process of reducing the seismic ground motion spectra to match with our site specific spectrum curve. It's called as spectral matching process, and that we need to do because whatever earthquake we are going to consider, whatever ground motion we are going to consider, that should be compatible with your site. Okay, so we have to scale down or scale up whatever required the earthquake. So here we have to choose the option match the two response spectrum, and we have to click add new function. Okay, so here there are basically we'll give the name later. There are basically two methods to use for spectral matching. One is spectral matching in frequency domain and spectral matching in time domain. So we'll select this spectral matching in time domain, which is quite works well. Target response spectra. Okay, so this is my target response spectra, that is Indian response spectra, which I have defined earlier. So I will show that part also. which we have covered in our last video. So I have already defined this response spectrum IRS 1893, where I have put my zone, my importance factor, soil type, response reduction factor. All those things are there. Okay. So go to define function, time history, match to response spectrum, add new function. Okay. So we have selected the spectral match in time domain. So this is the response spectrum. We have to select. This is my target response spectrum as per codal provision, and reference acceleration time history. Okay. So just a minute, all those time histories are gone. Just a minute, I will add 2080.002 ground motion x ground motion y ground motion z. Okay, view response spectrum, and we'll delete. Okay, we have seen all this. Now match to response spectrum, add new function, spectral match in time domain. Okay, so IS Indian response spectrum 1893. So this we will select, and first we'll match with x direction, y direction, and then z direction. Okay, the response spectrum acceleration unit is in G, and the time history acceleration unit. So here you can see the time histories are given in centimeter. Okay, so we have to select here centimeter. Now here set or match time history is the option. So we have to click here match time history. Now this time history will be matched with our target response spectrum, because that type of earthquake will occur there. If your structure is in zone 2 and you are taking any ground motion from zone 5 or zone 6, so that is not a realistic. So we have to match, and this is very important process. So it may take some time. Okay, here you can see this was the actual ground motion, which is shown in blue color, and so this is the brown color. This is the scale down earthquake, which is the realistic demand for that particular site. Okay, now here you can see this is the actual ground motion. This is the actual response spectra of that earthquake, and I will show you. Yes, for plot for matched time history. So here you can see this is the response spectrum curve from IS 1893, and this is the response spectra curve of that earthquake, and which is quite well scaled down and which is quite well matched with this response spectra. Okay, so that means we have accurately matched. Okay, now we will give the name here. So TH spec X, okay, spectral time history, which is scaled down basically. And here you have to convert to user define. Okay, so what happened here is ETAB has now saved this scale down earthquake. Okay, so no problem if even these earthquake records are now not with me, this is saved in your ETAB. Similarly, we have to do the process for Y and Z. So I will quickly do that part. So it takes a few seconds to complete the matching. Yes. So convert before that we'll give the name here th spec y, convert to user define. Similarly we'll do for z direction earthquake. Now the next step will be we have to create the load cases, that is time history in x direction, y direction and z direction. Yes, so we'll give the name here th spec z, convert to user define, click on OK. Now go to define load cases. Now here we will create the load case. So go to add new case. Here we have to give the name to the load case. So th x y, that is time history case x and y, means we are putting the time history or ground records in both x and y direction. So here you have to select the time history analysis, and there are multiple ways. As we are going to do the linear analysis, you can go with linear model. Mass source, which we have already defined, you can check our previous video on seismic analysis. The link is in the description box. Then here click on add. So we have to apply the loads. At load pattern, select acceleration, u1, function. Now function, we have to select the scaled time history. So th spec x, and here we'll keep the scale factor in G units, 9806. Similarly, acceleration U2, spec Y, 9806. Modal load case, we'll keep modal, time history, motion type, transient, number of output time steps. So there are 2000 points basically in that time history, and each point is of 0.02. Okay, that means it was a 40-second earthquake, and standard is output time step standard is 0.1. That means we will take 400 output time steps. So basically ground motion uh, seconds, how much long earthquake was, divided by output time step size, that is 0.1, you will get the answer. Modal damping is 5%. So click on OK. Then add copy of this case. Here instead of xy we will give the name yx, and instead of u1, or instead of spec x in u1 direction, we will apply spec y, and for u2 direction we will apply spec x. Means we are changing. In u1 direction we will now apply the time history of y direction, and for u2 will apply the time history of x direction. Okay, remaining things will be as it is. Then again we'll apply the time history case for z direction. So time history, linear model, add acceleration u3, 9806, and here the number of points will be 400. Click on OK, click on OK. Now go to analyze and run analyze, and wait for the analysis to complete. Yes, so go to tables, go to tables, analysis results, structure output, base reaction, show table, right click, show table. So here you can see equivalent static earthquake, equivalent static method, base shear is 92.6977. Okay, and earthquake, that is time history x and y direction, the one is maximum, one is minimum. That means it is moving in both positive and negative direction. We have to consider the absolute maximum, that is 63. Okay, that means it is less than earthquake in x direction. So we have to scale up the base shear, and which is a provision in our IS code also. Okay, so there is a clause in IS code that even after you perform the time history, you have to scale up your base shear as we do in our response spectrum analysis. Yes, here you can see dynamic analysis may be performed by either time history method or response spectrum method. Okay, and then here you can see when VB is less than VB bar, the force response quantities shall be multiplied by VB dash upon VB for earthquake shaking considered along. So this is the clause basically. That that's why we need to scale up the base shear. So here the value is 63.1551 for THXY in X direction. Okay, basically we will get the base shear in both direction because we have applied the time history or ground motion in both direction. Okay, so to scale up we have to open here the calculator. The value for earthquake in X direction, that is Fx is 92.6977 divided by the maximum of these two THXY is 63.1551. So this is my factor. So I will copy this. Okay. So this factor I will apply to U1. Okay. Similarly, earthquake in Y direction. So earthquake in Y direction, again it is 92.6977, 92.6977 divided by THXY. THXY, the maximum here, the absolute maximum value is 44.8702, 44.8702. So this is the value we have to apply in our YU2. This is the value. Similarly, we have to check for THYX case. So for THYX case, the maximum is 61.0848 and by equivalent static method it is 92.6977 divided by 61.0848. So this is the scale factor we have to select. So that will be applied for X direction, that is U1. And now the last is again the maximum of these two is 46.0339. Out of these two, the absolute maximum value is 46.0339. So again I will clear 92.6977 divided by 46.0339. So this is the factor. Copy. I will copy this in notepad. Y direction, that is U2. Okay, now respective scale factors we need to put in our time history case. So go to define load case THXY, modify. Okay, for U1 we have to use this scale factor. So into and for U2 direction I'll copy into click on OK. Similarly THYX here for U1 I'll copy this and for U2 click on OK. And for modification in Z direction we have to consider the maximum one which is written in this point. The vertical Z direction, the multiplication factor shall be taken as maximum of these two. So the maximum factor is 2.06. Okay, so this is the maximum factor. We will select, click on OK, click on OK, click on OK. Now analyze and run analyze our model. Now we have to check that our base shears are matched, that is the base shear obtained from time history analysis is equal to base shear obtained from equivalent static method. So we'll check that in analysis, go to structure output, base reaction, right click, show tables. So here you can see this is 92.6977 base shear is there. Okay, for time history X it is here 85 and here it is 93. Okay, and for THYX it is, sorry, here you can see it is 93, here it is 92.69. Okay, similarly here 93 and 91. So this 91 is slightly lesser basically. So you can repeat this process. This is the iteration. You have to do it once again so that these values are exactly matched. Okay. Now go to display. We are going to see the results. This option combined story response plot. You have to click here. This option is basically for time history. Okay, here you can see the input function. Here this is the your ground motion. Here this is the story response, that is displacement. First graph, second graph is of drift, third graph is of shear, and fourth graph is of overturning. Okay, and here you can click on animate. Once you click on animate, it starts the time history and the red point shows the acceleration point, and related to that how the building is responding, it's shown here. Okay, you can increase the speed of the animation and you can check the response of the structure. This red color is the maximum positive response and this green color is the maximum negative response, and this is same for all the graphs, that is remaining drift, shear and overturning. Okay, this is how you can check the results. Okay, so this is it from time history analysis. You can check other results also, like floor, uh, story forces, torsion, and all those things you can check. Or we'll make a separate video in which we will cover all the dynamic results comparison. Okay, I hope the concept is clear to you. Please like, share, subscribe the channel. Thank you so much.